welcome back. This is in continuation with our previous lecture of digital filtering. In the last lecture, I have told you that there are two types of filters which we do employ. One is a low pass filter, the other one is a high pass filter. The combination of these two will be a band pass filter and a band stop filter. And you do have two approaches to design these low pass filter and high pass filter. One is a finite impulse response filter, which we call it as an FIR. The other one is an infinite impulse response filter. Both of this can be employed for filtering in numerical relays. Now, the first one is here FIR filters. You know that digital filters are linear systems, and their impulse response completely characterizes any linear system. Now, if your impulse response, whichever you are taking for your filtering activity, if it consists of finite number of terms, then the filter is called as finite impulse response filter. If you are going to take infinite number of terms in your impulse response, then it is called as your infinite impulse response filter. That is the only difference between your finite impulse response and infinite impulse response filters in terms of your inputs. Now, see here, this is your FIR digital filter. This you might have already gone through. So, a quick review, I won't take much of your time in this video lecture. So, this is your present input xn. So, what you will be doing is nothing but you will be taking impulse responses. See, whatever the output which you want to take from this signal xn, this is 1 A0 into xn, and also you will be taking these are the delays which you are creating here. Okay, see how many number of delays you want to create, you can create it, and for each of these impulse response you need to take some coefficients. So your output is nothing but it's not only it is a function of your present state, but also it is a function of your previous state also. We have already seen for a low pass filter what it is. Right, for a high pass filter it is minus, right? The only difference is that the coefficients are going to change. What I told you in the earlier lecture, you can go with some equations or something like this, right? So it is just like your combination of different samples of the signal. This is your output state. So that is what which I have tried to mention here. Okay, so this is your finite impulse response digital signal. The coefficients values they will be changing here. What I have represented here, A0, A1, A2, like that. Up to how many number of samples which you want to take, you can take it. Okay, so the filter generates output samples by forming a weighted sum of the input sample and a limited number of previous input samples. The simplest one, you can just take A1 and A0 as 1, and you can take an average, 0.5 and 0.5. That's the simplest thing. The weights are nothing but samples of impulse response of the filter. So if I represent it as an equation, so this is your expression of your output of your filter. Okay, so it is just your convolution of the incoming samples with the impulse response. Okay, so this is your mathematical expression. This is your frequency response of that particular signal. Okay, so if you carefully see, you need to store the data. So you need to store at least m samples if you are designing the filter for m samples. So you need to store m samples, and also m plus 1 coefficients also you need to store. Okay, so you do need some memory for performing this particular action. If you want to be more accurate, you should go with higher number of m. So automatically your memory requirement will be increasing. Okay, so the frequency response will be this one. This is the generalized expression. If you carefully see, m is the number of samples which you want to consider. Okay, and see, this is the sampling time, and this is the coefficients, the coefficients which you want to take. Modern day computers, they automatically give you coefficients by observing the signal. But if you are doing it manually, then you are supposed to mathematically model it, and then you are supposed to determine the coefficients. Okay. And if you carefully see, the frequency response is a periodic function, and it is a period of 2 pi by delta t, and It is just like your Fourier response, right? So whatever the impulse response which you do have, you are applying it for Fourier transform. This is the transfer function in Z domain. Okay. You want me to explain this one? I think this is the sample x of n. So how will you get the previous sample? This is right. So this is xn zn minus 2. So if I take xn common and bring it to this side, then this is yn by xn. So what you will be getting? You will be getting a0 plus a1 z inverse plus a2 z inverse whole square. So I think I don't need to explain all these things. You might have already covered these things. Okay. So this is the representation. Okay. And the next one is infinite impulse response filter. Here, the major difference is that your present state of your, in the earlier case, it was a function of your present state and the previous state of the signals, right? But here, it is also a function of the previous state of the outputs also. This is the major difference between your finite impulse response and infinite impulse response. Okay. So here the coefficients I will take it as A1, A2, A3. Here I will take the coefficients as B1, B2, B3. Okay. See, the filter is characterized by the fact that nth sample of output is formed by using previous values of both inputs and outputs. Earlier case we used to take only inputs. Now we are taking both inputs and outputs. And for inputs representation, I'll take this A0 and A1. It is just like your FIR filter. Additionally, I'm taking these coefficients. It will make you just like a recursion format of it. Okay. There are so many ways for implementation of these things. So this is a canonical form of representation. Up to here, this is your FIR filter. Additionally, what I'm doing it, I'm taking feedback of my output also. Okay. So the working, if you carefully see, the output is a function of m number of passed inputs and k number of passed outputs. The choice is yours. What is the value of m and k? And if you carefully see, it has feedback. And so it can be considered as a recursive one also. This is the transfer function. And this is going to be stable if the output is a non-increasing sequence. Okay. If it is increasing, then it will lose its stability. Okay. So the major differences I have listed out here. FR filter, it is a function of only passed inputs, whereas IR filter, it's a function of passed inputs and also passed outputs, and hence it is considered as a recursive one, whereas this is not considered to be a recursive one. Here the impulse response is finite, here it is infinite. Since there is no feedback, this always remains stable, but whereas it may vary depending upon your feedback. The number of coefficients is limited. You do have from A0 to AM, but here, apart from this, you do have from B1 to B1 also. It is having denominator terms also, but whereas here you will be getting only numerator terms, and that too they are dependent on inputs. But here, both are input and also outputs. And also, you do require a higher order filter for this one, but whereas here you do require a lower order filter. Okay. And it has a very linear phase response, as already I mentioned it in the very first slide. But whereas this will be having a non-linear phase response. These are out of your UG complex. So you forget this slide, but for the previous slide, you mentioned at least one or two differences when I asked in the examination. This is your representation of your transfer functions, and this is in Z domain. It is very easy to implement, so that's why I have mentioned it here. But whereas this is a little bit hard for you to implement. So on the whole, I can say that digital filters nowadays, they are finding their way into this numerical relays. So they are very important component in your numerical relay. Okay, and also they play a very important role in analyzing your signal and filtering out your unwanted components. Okay, so we'll try to discuss more in the class. I hope that now you are able to describe the different filters, and in particular, what are the advantages of digital filters. Okay, so these are the sample questions which I'll be asking you, and we'll discuss more in the class.